For a local constant estimator, bandwidth is the main tuning parameter. A narrow bandwidth uses a small neighborhood, giving lower smoothing bias but higher variance. A wide bandwidth pools more observations, lowering variance but potentially averaging across real changes in the conditional mean. Both bias and variance shrink with a growing sample, but they respond differently to bandwidth. Prediction, point estimation, and confidence intervals may therefore call for different bandwidth choices. Think of bandwidth as the radius of attention. If it is very small, the curve follows local noise and overfits. A moderate value is smooth yet responsive. A very large value resembles a global average or line and may wash out important features. Showing sensitivity to several defensible bandwidths is part of the substantive analysis, not a graphic afterthought. If a conclusion appears only for one finely tuned bandwidth, it is not a robust feature of the data. The rate calculation explains why non-parametric estimation is slower. Variance depends on how many observations fall in the local window, roughly the sample size times the bandwidth. Bias depends on how far the averaging extends. In one dimension, balancing the leading terms gives a bandwidth shrinking at the fifth root rate and an estimation error shrinking more slowly than the familiar parametric square root rate. With more covariates, local neighborhoods empty rapidly, producing the curse of dimensionality. Here is the algebra behind that rate. For a one-dimensional local constant, squared bias is proportional to the fourth power of bandwidth, while variance is proportional to 1 over the sample size times bandwidth. Equating the two gives the fifth root bandwidth and a root mean squared error shrinking at the 2/5 rate. The lesson matters more than memorizing exponents. Local flexibility costs information, so non-parametric estimates converge more slowly than correctly specified parametric ones. Local polynomials can be written as linear smoothers, but their weights need not all be positive. The weights sum to 1 and satisfy moment conditions that remove local slope or curvature. Near an endpoint, data exist mainly on one side. A local constant, then, has one-sided bias, while a local linear fit estimates both a level and a slope and uses the intercept as the target. That built-in boundary correction explains why local linear regression is the usual default. Interior points have observations on both sides, but a boundary or regression discontinuity cutoff creates a one-sided problem. A local constant averages an asymmetric neighborhood. If the conditional mean has a slope, that average is not centered on the target and is biased. Local linear regression estimates the slope and removes this first-order component. The same reason makes it attractive both at the natural edges of a support and on each side of a policy cutoff. Why can some local linear weights be negative? The weights must sum to 1, but they must also make the weighted covariate deviations balance at 0. In the interior, mostly positive weights can satisfy both conditions. Near a boundary, the missing observations on one side may require some negative weights to restore balance. Those weights are not a numerical failure. They are the mechanism that corrects local slope bias while preserving the target level.